combinational logic circuits for digital system may be combinational or sequential. A combinational circuit consists of logic gates whose outputs at any time are determined from only the present combination of inputs. A combinational circuit performs an operation that can be specified logically by a set of Boolean functions. In contrast, sequential circuits employ storage elements in addition to logic gates. Their output are a function of the input and the state of the storage element. Because the state of the storage element is a function of previous inputs, the outputs of a sequential circuit depend not only on present values of input but also on past inputs, and the circuit behavior must be specified by a time sequence of input and internal stages. Sequential circuits are the building blocks of digital systems. First of all, we discuss combinational circuits. A combinational circuit consists of input variables, logic gates, and output variables. Combination logic gates react to the value of signals at their input and produces the values of the output signal, transforming binary information from the given input data to a required output data. A block diagram of a combinational circuit is shown in this figure. The n input binary variables come from an external source. The m output variables are produced by the internal combinational logic circuit and go to an external destination. Each input and output variable exists physically as an analog signal whose values are interpreted to be a binary signal that represents logic 1 and logic 0. In many applications, the source and destinations are storage registers. If the registers are included with the combinational gate, then the total circuit must be considered to be a sequential circuit. For example, if we take an example of a fuel tank and we have two inputs, high and low, it means if fluid level is too high, then input is 1, otherwise high input remains low, and low input means if the fluid level is too low, then it remains 1, otherwise after level goes too high, it becomes 0. Similarly, it has two outputs, pump and drain. If the fluid is going into the tank, then the pump is it means the pump is running and the output is 1, otherwise output is 0. Similarly, if the tank is overflowed, then the pump is 0 and the drain output is 1, otherwise drain output is 0. Input and output relationship, as we discussed here, is described by a truth table. If we build a truth table of these two inputs and the outputs, we see that at input level, we have two inputs, high and low. If both are 0, 0, it means neither drain nor pump are running. It means tank level is okay. If high input is 0 and low input is 1, it means tank is empty and then we need to run the pump. So the output is pump is equal to 1 and drain is equal to 0. Low level pump more in. Similarly, if the fluid is too high in the tank, then the high input becomes 1 and low input becomes 0. In this stage, pump output is 0 and the drain output is 1. High level drain sum out. If both inputs are 1, 1, then neither pump nor drain is running. Input cannot occur. This is called a down care condition. We also represent this truth table into the circuit diagram. To build a circuit diagram from this input, we need two AND gates and two inverted inputs. Analysis of a combinational circuit. The analysis of a combinational circuit requires that we determine the function that the circuit implements. This task starts with the given logic diagram and culminates with the set of Boolean functions, a truth table, or possible an explanation of the circuit operation. If the logic diagram to be analyzed is accompanied by a function name or an explanation of what it is assumed to accomplish, then the analysis problem reduces to a verification of the state function. The analysis can be performed manually by finding the Boolean functions or truth table or by using a computer simulation program. The first step in the analysis is to make sure that the given circuit is combinational and not sequential. The diagram of a combination circuit has logic gates with no feedback path or memory elements. A feedback path is a connection from the output of one stage to the input of a second gate that forms part of the input to the first gate. Feedback path is a digital circuit defined as sequential circuit and must be analyzed according to procedures. Once the logic diagram is verified to be that of a combinational circuit, one can produce to obtain the output Boolean function or the truth table if the function of the circuit is under investigation. Then it is necessary to interpret the operation of the circuit from the derived Boolean function or a truth table. The success of such an investigation is enhanced if one has previous experience and familiarity with the wide variety of digital circuits. To obtain the Boolean function from a logic diagram, we produce it as follows. Label all gate output that are a function of input variables with arbitrary symbols but with meaningful names. Determine the Boolean function for each gate output. Number 2, label the gate that are a function of input variable and previously labeled gate with other arbitrary symbols find the function of these gates. Number 3, repeat the process outlined in step 2 until the output of the circuits are obtained. By repeating substitution of previously defined functions, obtain the output Boolean function in terms of input variables. The analysis of a combinational circuit of this figure illustrates the proposed procedure. We note that the circuit has two inputs, X and Y. So by following the analysis step, first of all, we label all gate outputs with symbols. At first NAND gate, we label the output of first NAND gate is as T1, which is produces by X and Y after ANDing both X and Y. Similarly, we label the outputs of second stages NAND gates and we name them T2 and T3. Similarly, T2 is produces by multiplying the X input with T1 output of first NAND gate, and similarly the output T3 of the second stage NAND gate is produced by multiplying Y input with output T1 of the first stage NAND gate. And in the last, for the last NAND gate, we label the output as is equal to F, which is produces by multiplying both second stages NAND gates that are T2 and T3. After that, find Boolean function for all gates. We write the Boolean function and when we write it from last to first stage is that is equal to F is equal to T2, T3 whole complement, and then we put the values of T2 and T3, that is xt1 complement into yt1 complement. Then we put the value of T1, that is x and y complement, so it becomes x into xy complement plus y into xy complement. After simplifying this Boolean function, we get a simple algebraic form, that is f is equal to x inclusive y. Similarly, we have another example. In this example, the question is what are the output functions of F1 and F2? The analysis of the combinational circuits of this figure illustrates the proposed procedure. We noted that the circuit has three binary inputs A, B, and C, and two binary functions, outputs F1 and F2. The outputs of various gates are labeled with immediate symbols. The output of gates that are a function only of input variables are T1 and T2. Output F2 can easily be derived from the input variables. The Boolean function for these three outputs are as: first of all, F2 is equal to AB plus AC plus BC. T1 is equal to A plus B plus C. T2 is equal to A, B, and C. Next, we consider outputs of gates that are a function of already defined symbols. T3 is equal to F2 complement T1 and F1 is equal to T3 plus T2. To obtain F1 as a function of A, B, and C inputs, we form a series of substitutions as follows. F1 is equal to T3 plus T2 is equal to F2 complement T1 plus A, B, and C is equal to AB plus AC plus BC whole complement into A plus B plus C plus ABC. After simplifying this, we get the result F1 is equal to A complement B C complement plus A complement B complement C plus A B complement C complement plus A B and C. If we want to pursue the investigation and determine the function transformation task achieved by this circuit, we can draw the circuit from the derived Boolean expression and try to recognize a familiar operation. The Boolean function for F1 and F2 implement a circuit of a full adder circuit. Merely finding a Boolean expression of a circuit does not provide insight into its behavior, but in this example, we will observe that the Boolean equation and truth tables for F1 and F2 match those describing the functionality of what we call a full adder. The derivation of truth table for a circuit is a straightforward process once the output Boolean function are known. To obtain the truth table directly from the logic diagram with sorry, logic diagram without going through the derivation of Boolean function, we proceed as follows. Determine the number of input variables in the circuit for n inputs from the 2 to the power n possible input combination and list the binary number from 0 to 2 to the power n minus 1 in a table. It means if we have 3 inputs, then 2 to the power n is equal to 2 to the power 3 is equal to 8 combination. So our input produces 8 combinations and it starts from 0, 0, 0 and at 1, 1 and 1. Second, label the output of a selected gate with arbitrary symbols. Number 3, obtain the truth table for the outputs of those gates which are a function of the input variables only. Number 4, proceed to obtain the truth table for the outputs of those gates which are a function of previously defined values until the columns for all outputs are determined. This process is illustrated with the circuit diagram of our previous example. In this table, we found the 8 possible combinations for the 3 input variables. The truth table for F2 is determined directly from the values of A, B, and C. with F2 equal to 1 for any combination that has 2 or 3 inputs equal to 1. The truth table for F2 complement is the complement of data F2. The truth table for T1 and T2 are the OR and functions of the input variables. Respectively, the values for T3 are derived from T1 and F2 complement. So T3 is equal to 1 when both T1 and F2 complements are equal to 1, and T3 is equal to 0 otherwise. Finally, F1 is equal to 1 for those combinations in which either T2 or T3 or both are equal to 1. Inception for the truth table combination for A, B, C, F1 and F2 showed that it is identical to the truth table of the full adder given in our next section for X, Y, Z, S and C respectively. Another way of analyzing combination circuit is by means of logic simulation. Design procedure of a combinational circuit. The design of combinational circuits start from the specification of the design objective and culminates in logic circuit diagram or a set of Boolean functions from which the logic diagrams can be obtained. The procedure involves the following steps. Number one, from the specification of the circuit, determine the required number of inputs and outputs and design a symbol to each. Number two, draw the truth table that defines the required relationship between input and output. Number three, obtain the simplified Boolean function for each output as a function of the input variable. Number four, draw the logic diagram and verify the correctness of the design manually or by simulation. A truth table for combination circuits consists of input columns and output columns. The input columns are obtained from the 2 to the power n binary numbers for the n input variables. The binary values for the output are determined from the static specification. The output functions specified in the truth table give the exact definition to the combination circuit. It is important that the verbal specification be interpreted correctly in the truth table, as they are often incomplete and any wrong interpretation may result in an incorrect truth table. The output binary function listed in the truth table are simplified by any available method such as algebraic manipulation, the MAP method, or a computer-based simplification program. Frequently, there is a variety of simplified expressions from which to choose. In particular application, certain criteria will serve as a guide in the process of choosing an implementation. Practical design must consider such constraints as the number of gates, number of inputs to a gate, propagation time of the signal through the gates, number of interconnections, limitation of the driving capability of each gate, and various other criteria that must be taken into consideration when designing integrated circuits. Since the importance of each constraint is dictated by the particular application, it is difficult to make a general statement about that constitutes an acceptable implementation. In most cases, this simplification begins by satisfying an elementary object such as producing the simplified Boolean function in a standard form. Then the simplification process proceeds with further steps to meet other performance criteria. Design combination circuits, logical minimization, number of gates, number of inputs to gate, propagation delay, number of interconnection, limitation of driving capabilities. Uh, Code conversion examples, the availability of a large variety of codes from the same discrete element of information results in the use of different codes by different digital systems. It is sometimes necessary to use the output of one system as the input to another. A convergence system, a convergence circuit must be inserted between the two systems if each use different codes for the same information. Thus, a code converter is a circuit that makes the two systems compatible even though each use a different binary code. To convert from binary code A to binary code B, the input lines must supply the bit combination of elements as specified by code A, and the output lines must generate the corresponding bit combination of code B. A combination circuit performs this transformation by means of logic gates. Design procedure will be illustrated by example that converts binary coded decimal BCD to excess 3 code of the decimal gates. We already discussed these two binary coded systems in chapter 1. The bit combination assigned to the BCD and excess 3 codes are listed in this table. Since each code uses 4 bits to represent a decimal digit, there must be 4 input variables and 4 output variables. We designate the 4 input binary variables by the symbols A, B, C, and D, and the 4 output variables by W, X, Y, and Z. The two tables relating the input and output variables is shown in this figure 4.2 of our chapter 4. The bit combination for the input and their corresponding outputs are obtained directly by using our knowledge of chapter 1. Note that 4 binary variables may have 16-bit combination. 2 to the power n is 2 to the power n is equal to 2 to the power 4 is equal to 16, but only 10 are listed in the truth table. The 6-bit combination not listed for the input variables are don't care combination. These values have no meaning in BCD, and we assume that they will never occur. Therefore, we are at liberty to assign to the output variables either a 1 or a 0, whichever gives a simpler circuit. The maps are plotted to obtain simplified Boolean function. For the outputs, each one of the 4 maps represent one of the four outputs of the circuit as a function of the four input variables. The ones marked inside the squares are obtained from the minterms that make the output equal to 1. The ones are obtained from the truth table by going over the output columns one at a time. For example, the column under output Z has 5 ones, therefore the map of Z has 5 ones, each being in a square corresponding to minterm that makes Z equal to 1. The 6 don't care minterms 10 through 15 are marked with an X. One possible way to simplify the functions into sum of product form is listed under the map of each variable. A two-level logic diagram may be obtained directly from the Boolean expression derived from the maps. There are various other possibilities for a logic diagram that implement this circuit. The expression obtained from the K-maps may be manipulated algebraically for the purpose of using common gates for two or more outputs. The manipulation illustrates the flexibility obtained with multiple output systems when implemented with three or more level of gates. So after simplifying by using K-maps, we get Z is equal to D complement, Y is equal to CD plus C complement, D complement, and this gives us Y is equal to CD plus into C plus D whole complement. X is equal to B complement C complement plus B complement D plus B C complement D complement, and this gives us X is equal to B complement into C plus D plus B into C plus D whole complement. And at last, W is equal to A plus B C plus BD is equal to A plus B into C plus D. The logic diagram that implements these expressions is shown in this figure. Note that the OR gate, whose output is C plus D, has been used to implement partially each of three outputs. Not counting input inverters, the implementation in sum of product form requires 7 AND gates and 3 OR gates. The implementation requires 4 AND gates, 4 OR gates, and 1 inverter. If only the normal input are variable, the first implementation will require inverters for variable B, C, and D, and the second implementation will require inverters for variable B and D. Thus, the three-level logic circuit requires fewer gates, all of which in turn requires no more than two inputs. Binary adders. Binary adder and subtractors. Digital computers perform a variety of information processing tasks. Among the functions encounters are the various arithmetic operations. The most basic arithmetic operation is the addition of two binary digits. This simple addition consists of four possible elementary operations. 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 1, 0. The first three operation produces a sum of one digit, but when both GUND and addend bits are equal to 1, the binary sum consists of two digits. The higher significant bit of this result is called a carry. When the AND and addend numbers contain more significant digits, the carry obtained from the addition of two bits is added to the next higher order pair of significant bits. A combinational circuit that performs the addition of two bits is called a half adder. One that performs the addition of three bits, two significant bits, and a previous carry is a full adder. The name of the circuit stems from the fact that two half adders can be employed to implement a full adder. A binary adder subtractor is a combination circuit that performs the arithmetic operations of addition and subtraction with binary numbers. To develop this circuit by means of hierarchical design, the half-adder design is carried out first, from which we develop the full adder. Connectioning n full adder in cascaded produces a binary adder for two n-bit numbers. The subtraction circuit is included in a complementing circuit. From the verbal explanation of a half adder, we find that this circuit needs two binary inputs and two binary outputs. The input variable designated the AND and addend bits. The output variables produces the sum and carry. We assign symbols X and Y to the two inputs and S and C to the outputs. S stands for sum and C stands for carry. This simple addition consists of four possible elementary operations. 0 plus 0 is equal to 0 and 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 1, 0. The block diagram of a half adder is shown to the right side of the slide. The truth table for the half adder is listed in the previous slide, where the C output is one only when both inputs are 1. The S output represents the least significant bit of the sum. The simplified Boolean function from the two in outputs can be obtained directly from the truth table. The simplified sum of product expressions are as x is equal to x complement y plus xy complement, and the carry is equal to xy. The logic diagram of the half adder implemented in sum of products is shown here. It can be also implemented with an exclusive OR and an AND gate as shown below the block diagram. This form is used to show that two half adder can be used to construct a full adder. A full adder is a combination circuit that forms the arithmetic sum of 3 bits. It consists of 3 inputs and 2 outputs. Two of the input variables, denoted by x and y, represent the two significant bits to be added. The third input z represents the carry from the previous lower significant position. Two outputs are necessary because the arithmetic sum of 3 binary digits ranges in values from 0 to 3 and binary 2 or 3 needed 2 digits. The two outputs are designated by the symbols S for sum and C for carry. The binary variable S gives the value of the least significant bit of the sum. The binary variable C gives the output carry. The block diagram of a full adder is shown in this figure. The truth table for the full adder is listed. The 8 rows under the input variables designated all possible combinations of the 3 variables. The output variables are determined from the arithmetic sum of the input bits. When all input bits are 0, the output is 0. The sum S output is equal to 1 when only one input is equal to 1 or when all 3 inputs are equal to 1. The carry C output has a carry of 1 if 2 or 3 inputs are equal to 1. The input and output bits of the combination circuits have different interpretation at various stages of the problem. On the one hand, physically, the binary signals of the input are considered binary digits to be added arithmetically to form a 2-digit sum at the output. On the other hand, the same binary values are considered as variable of Boolean function when expressed in the truth table or when the circuit is implemented with logic gates. The maps for the output of full are shown in this figure. The simplified expressions are as S is equal to x complement y complement z plus x complement y z complement plus xy complement z complement plus xy and z. And the carry is equal to xy plus xz plus yz. The logic diagram for the full adder implementation in sum of product form is shown in this figure. It can also be implemented with 2 half adder and 1 OR gate. The S output from the second half adder is the exclusive of Z, and the output of the first half adder is given as S is equal to Z exclusive into X exclusive Y. The carry output is equal to C is equal to X Y complement Z plus X complement Y Z plus X